Hello everyone. From the previous chapter, we already talked about solving the second ODE in terms of series solution. In this chapter or in this video, it's gonna be another method to solve second ODE in terms of series solution. But this one is about Bessel's equation or Bessel method. This one is easier to find the answers in terms of series solution, which is we're gonna learn in this video. Okay, to get the answers in terms of series solution of Bessel's equation, first you have to know what is Bessel's equation. Just look at this form. This is a form of second ODE. Here we have x squared times d squared y over dx squared plus x times dy over dx plus, in this parenthesis, lambda squared x squared minus mu squared times y equal to 0. So whenever you have second ODE and you can rearrange into this form, then you can use the Bessel's method to solve the answers in terms of series solution. Okay, just remember this is very important. This is the form of Bessel's equation of order nu with a parameter lambda. Okay, lambda is here, nu is here. Okay, to solve this second ODE form, from the previous chapter we can use the Frobenius method to solve it, but in this chapter we can use the shortcut method, which is the Bessel's method to solve the equation, the second ODE here, and the answer is gonna be in this form, which is y is function of t is lambda x here, and equal to c1 times c1 is a constant, and j nu t j nu is a function of t plus c2 is constant, and times j minus nu t. Okay, this is similar to the Frobenius method, the answer for the Frobenius method. Okay, and the j nu and j minus nu is this one. Okay, j nu t is equal to this form, which is I'm not going to read it to you. This is because Bessel's function of the first kind of order nu. Okay, so it look like easier, when you can rearrange to get this form, and you know what's lambda, and you know what is nu, then you can get into this form. Okay, and for the j minus nu t equal to this summation form. Okay, but you don't need to remember this form because you're not gonna use it. Okay, but this one, the Bessel function of the first kind, is defined when nu is neither 0 nor a positive integer. Okay, out here. T is not a member of zeros or positive integer. Okay, then you can use j nu and j minus nu. Okay, but when nu is zeros nor a positive integer, okay, then we're gonna use n instead of nu. Okay, then the answer is gonna be in this form, which is yt equal to cn jn t plus c2 yn t. Okay, jn is called the same as previous slides, which is Bessel's functions of the first kind, and yn here is called Bessel's functions of the second kind of n. Okay, so you have to figure out what is the value of nu. Okay, nu. Okay, is nu is not zeros or positive integer. Okay, then we can use new. But if new is zeros or positive integer, then you have to use n instead of new, and the answer is in this form. I'm gonna summarize in the next slide, so don't worry about it. Okay, for the yn is equal to this form, okay, and equal to this long form. Don't need to remember it, just look at it. There is also modified Bessel's function, which is when you have second ODE in terms of this form, which is similar to previous slides, but this one you have the minus sign here. Okay, so whenever you have second ODE in terms of this form, which is x squared times d square y over the x squared plus x times dy over the x minus, in this parenthesis, x squared plus new square times y equal to 0, and this is the form of modified Bessel's function. Okay, and for this one we can rewrite into this form, which is x squared times d square y over the x squared plus x dy over the x. Okay, this is the same, plus from the minus sign here to plus sign here. In this parenthesis, I square, I is the imaginary number. Okay, times x square minus new square times y equal to 0, and this form there also be the form of the answers in terms of Bessel's equation. Okay, so in the case when new is neither 0 nor positive integer, then solution in terms of series solution is going to be in this form, which is equal to y x equal to c1 constant times j new of function ix plus c2 j minus new the function of ix. Okay, and you can rearrange into this form or whatever. And for the j new ix or j new of x, this is equal to this summation form. Okay, but again you don't need to remember this. And this function we call it modified Bessel's function of the first kind of order new. Okay, just we add modify in front of it. Okay, and when new is zeros or positive integer, then you have to write the answer in terms of this form, which is yx equal to c1 I, now it's going to be I n x plus c2 kn of x. Okay, and this is called the modified Bessel's functions of the second kind of order n. Okay, and kn equal to yn of function ix equal to here. Okay, and I new x equal to I to the minus new times j new ix, or equal to this summation. Okay, and you don't need to remember this. Okay, to get the answers, just look at this slide. This is a very important slide. Okay, so when we have second ODE, we can modify the problem into this form. Okay, and then you can find what is the value of new or n or p or s, whatever, so then you can answer the right answer. Okay, so this is the general form of second ODE. So whenever we have second ODE, just find the value of what is a, what is b, what is r, what is c, d, s, the b here, a, r, r here, okay, r here, okay. So the generalized form equal to x squared times y double prime plus x in this parenthesis a plus 2b x to the r times y prime plus in this parenthesis c plus d times x to the 2s, the 2s here, minus b times in this small parenthesis, which is 1 minus a minus r times x to the r plus b squared times x to the 2r times y equal to 0. So this you have to find what the value of a, b, c, d, and s and r. Okay. Then just in the case we can represent using z plus sign minus sign p. Okay. Of function x as one of the Bessel function. In this form, we haven't defined what is it's gonna be j, or it's gonna be y, or it's gonna be k. So we can just write z instead of in those values. Okay, and the general form is gonna be in like this. This is equal to yx equal to x power 1 minus a over 2, okay, times e to the minus bx to the r over r, okay, and times this parenthesis, which is c1 is constant, zp, p here is p equal to 1 over s times in this square root 1 minus a over 2 square minus c, okay, and this is the value of p. Okay, this is the function zp is a function of this is the function of in the square root absolute d over s times x to the s. It's not multiply, it's a function. Okay, just remember it. Some people confuse this is like zp times this function, which is wrong. Okay, cp is a function of square root in the absolute of d over s times xs plus c2 z minus p of this function, which is the square root of absolute d over s times x to the s. Okay, and then as I said, you have to find a, b, c, d, and s and r. So then you can figure out what is c value here. Okay, and the type of Bessel function that arise depend on the character of in this square root d over s and the value of p, which is when I'm gonna show you the summarize in the next slide. Okay. Okay, there are 4 cases here of the square root d over s. Okay, just go one by one. If square root d over s is real, so remember, and p is not integer or 0, then cp that's from previous slide, we can write in this form, which is j new, and for the z minus p, it's going to be j minus v, j minus new. Okay, and if for the second case, if square root d over s is real and p is 0 or integer n, okay, then zp we can write j n, and z minus p we can write yn. Okay, and for the third case, if the square root d over s is imaginary, which is the modified Bessel function, and p is not integer or zero, then zp we can write uh, j I new, okay, I new, and z minus p we can write I is imaginary, just remember it, I minus new, okay. And the last case, if the square root d over s is imaginary and p is zeros or integer n, okay, then zp we can write in, I is a modified Bessel function, an imaginary number, okay, and the z minus p we can write kn, okay. So now here is you have to remember this, okay, which is the four cases of the Bessel's function, okay. Now look at this example. Here we have x squared times y double prime plus x times in this parenthesis, which is 4 times x to the fourth minus 3 times y prime plus 4x to the eighth minus 5x squared plus 3 times y equal to 0. So this is the problem of secondary. So then from here you have to figure out what is the value of a, b, c, and r and s, okay. From the formula from the previous slide that we already talked about, then you have to figure out yourselves what is of this value, okay. Just compare the constant or coefficient with in front of y, y double prime, y prime, and y, and you see what's the value of this. So from here we get a equal to minus 3, b equal to 2, I equal to 4, c equal to 3, d equal to minus 5, and s equal to minus 1. So next, what you do is you find the value of the square root d over s. D is minus 5 over s is 1. So because in the square root is minus, there's minus sign, so it's gonna be imaginary number, okay. So it's the minus I5, okay, equal to minus I5. This is imaginary number. So then p is equal to 1 over s, it is square root of this 1 minus a over 2 of this square minus 3. So when you substitute all these value, you get equal to 1. So p equal to 1 in this case. So when you compare the value of square root d over s and the value of p, you're gonna see that this is the case number 4, okay, case 4, which is uh, the imaginary and p is the positive integer, okay, p is positive integer, so it's case number 4. So in this case we can write the zp, cp is gonna be I and k, okay, and the subscribe here is p equal to 1, right? So it's gonna be 1 here, 1 for I1 and k1, okay, and the rest is here, which is x to the just look at the previous slide and plug in is constant, x to the 1 minus 3 minus 3, so which is a over 2 times e to the minus in this parenthesis 2x to the fourth, which is x to the r over r, okay, time in this parenthesis of this function c1 I1, case number 4, of this function, which is the absolute of minus 5 times x power 1, okay, over 1 again, plus c2 k1 of this function, which is the square root d over s, which is minus 5 over 1 times x to 1, x to the s, which is s equal to 1. So then you can simplify this case 4 to here, which is x squared times e to the minus x to the 4 over 2 times, in this parenthesis c1 I1 of function x times square root 5, okay, plus c2 k1 of function x times square root over 5. So in some cases, when you know the value of x, you can substitute x in this form. Then maybe you can solve to get c1 and c2. Then you can find the value of y, okay, to get the answer. If you have initial condition or the boundary condition to solve c1 and c2, okay. And I also will give you a table to look to find the value of this, the I1 I0, J1 J0, K1 K0, or whatever. Or this is it's a long summarized table of the Bessel's equation. Okay, I'll give you in the folder. Okay, just look at it. Okay, now look at these examples that we use Bessel's equation to solve a problem in transport phenomena. Okay, in this system we have a fin. This is like heat exchanger. Actually, there are many fins of this system, but I will just show you only one small fin of this system. Okay, this system look like a pyramid. Okay, like we call it wedge shaped fin. Okay, this fin has length of L. W is the width of the fin, of the base, the fin base. Okay, and the height is H. Okay, and if we define along this axis to be x, this is x-axis, let's say this is x-axis, the original is here at the tip of the fin, which is x is equal to 0 at the top, okay, and along the x, okay, is the temperature is different, and the heat source is from the wall. Okay, this is TW. TW let's say this area is hotter than the outer temperature, which is the ambient temperature, TA. TA is ambient temperature. Okay, and this fin used to release the heat from the wall. Okay, as you see, it's increase the surface area of the system, so the heat can release more if you have like a large surface area. Okay, and if we divided this angle, of the tip into two theta, let's say this equal angle, theta and theta. Okay, and also if we divide the x-axis in small distance, let's say delta x. So from here, x equal to 0 to x, and x to x plus delta x. Okay, this is delta x is very small distance from the original from here. And okay, from this system, if we wanna find the temperature change or temperature profile along the x-axis, so we have to form formula of the temperature along this axis, from x-axis. To formulate the formula, you have to know the Fourier law of heat conduction and also Newton law of cooling. Okay, because the heat does conduct between along the x-axis, and there are also heat loss from the surface. Okay, that's Newton law of cooling, and for the conduction is Newton law of heat conduction. Okay, so for some of you already learned transport phenomena or the heat transfer, then you have to revise this chapter or this study. Okay. Okay, now let's do a mini review about Fourier law of heat conduction. Okay, if you remember Fourier law of heat conduction saying Qx equal to minus k dt over the x. Okay, Qx is the heat flux. Okay, the heat flux is mean the rate at which heat flows through an area is proportional to the area and to the temperature gradient in the direction perpendicular to that area. Okay, just imagine if we have heat source, heat source one, let's say A to B, heat flowing from A to B. The heat flux, it means we have to consider that the heat that flowing through an area that the cross-section area between A and B. Okay, just cross-section that we consider just one small cross-section. Okay, that's we call heat flux. And K here, K is the thermal conductivity, it's constant. dt over the x is the temperature gradient along the x-axis. Okay, or the temperature gradient along the x or along the axis that we consider. Okay, but in this case we consider only x axis, so it's going to be dt over the x. So the minus sign is to show that the heat flow from the hotter area to cooler area. Okay, so that means if qx is negative, that means the temperature is up in the x direction. Okay, qx is negative, that means the temperature increased in the x direction. So if qx is positive, that means dt over dx here is negative times negative is positive, right? So qx is positive, that means the temperature is down, temperature decrease in the x direction. Okay, so this is the Fourier law of heat conduction. We have to use this theory to formulate a formula that heat is flowing from the wall of the system, from the previous slide. Look at the wall to the tip of the fin. Okay, because heat is flowing from the hot air, which is the wall, to the tip. Okay. Okay, for the Newton law of cooling, saying here dt over dt, T capital is T temperature, dt, T small here is T time equal to H. H is time, heat transfer coefficient, time T minus T0. T here is the temperature at the surface. Okay, and T0 is the temperature at the surrounding or the temperature outside the system. Okay, and this equation dt capital over dt small is the rate, is showing the rate at which the heat is lost from an area on the surface of a body is proportional to the area and to the difference between the surface temperature of the body and the temperature of the surrounding medium. Okay, when you think about a system, or just think about the pin from the system we have, the heat also lost, from the surface, along the surface, everywhere along the surface. Okay, with the time. If the heat source, let's say the TW is generated continuously, then at the steady state, we can say the rate of the heat gain equal to the rate of heat loss. That means when we do the rate of heat gain minus the rate of heat loss is gonna be equal to 0. Okay, that's the steady state. Okay, we can use this Newton law of cooling to formulate the temperature profile along the fin that we're gonna do in this problem. Okay, now let's consider the heat conduction term again. Okay, and consider with the system that we have, which is the fin. Okay, this is the fin we have is just one fin, right? Okay, this is length L, and since we consider at this x plus delta x, okay, for the heat conduction, which is the heat is flowing from the wall, which is from x plus delta x to x, okay, it's kind of the opposite, okay, the opposite from of x equal to 0. And when you think about the conduction term, you have to think about the area that heat flowing through, okay. There are two cross-section area, which is at the cross-section area as x plus delta x, and also the cross-section area at x, okay. Okay, at the cross-section area x plus delta x is the input rate, okay. It's the input because it's flowing from TW to the tip. And for the output rate, because it is after flowing in at x plus delta x, and the output is going to be at x, okay. So you have to find to formulate the area at two cross sections, okay, cross section at x plus delta x and cross section at x. That means this is length L, we already know, but we don't know the width at this cross section, at this one and this one, okay. So this I'm gonna show you in the class, okay. Some of you can prove it how to get this length of W, okay. It's not W because it's shorter. If you think about it, it's shorter, okay. For the input rate, okay, input rate is Q times L. L is the surface area, it's cross section area at x plus delta x, as I said, the input rate. And Q, we just take it here, time here is the cross section area, which is L times W times x plus delta x over h, which is the cross section at this length, okay. This length I'm gonna show you in the class, okay. And the output rate is the shorter one, this one, the cross section area at this x, okay. It's gonna be Q times cross section area at x, which is Q times L. L is the same because the length is the same, times the shorter width, you know, W here but it's shorter, which is equal to x times W over h, okay. We can prove it if you know like the angle, and you know the triangle relation. You can prove it to get W here is equal to x times W over h, and this is also the same, x plus delta x times W over h, okay. And for here, since we assign that x equal to 0 at the tip, and here is equal at the wall, here is x equal to x, okay, x equal to x. So that means it's the opposite side that heat flowing, because it's heat flowing from the TW to the tip. So that means here, just read here, since we assign the origin x equal to 0 at the tip of the fin, so that the conduction term here must be the opposite side because it's the opposite direction of the heat flowing. That means because Q is always, it should be, it must be positive value, okay? So that means we have to add a minus sign in order to get the positive value, okay? So the input rate keep the same, but we have to add the minus sign here, okay? The output also the same, we have to add the minus sign here, okay? So now we get the input rate, the output rate of the heat conduction term. So now we can start to formulate the temperature profile. Next, you have to consider the convection term, which is the Newton law of cooling. Okay, there's only one output rate. Okay, because the heat loss from the surface area of the fin. Okay, that means gonna be the output rate is gonna be dt capital over dt. Okay, the temperature gradient with the time temperature gradient time the areas of both surface. Okay, it's gonna be equal to the Newton law of cooling is h times t minus ta. Okay, and here the surface area of the fin, which is x times delta x times L over cos theta. Okay, this one I'm going to show you in the class how we get this. Okay, just think this is the surface area of both sides of the fin. Okay, and on the side, the small side, we just ignore it because it's very small. Okay, then we have to combine from the Newton law of cooling and the heat conduction term together. Okay, the input, okay, the input is this term. Okay, for the conduction term, the output is this term. Okay, the output is we have to add minus sign, the minus sign. Okay, from the heat conduction, and also the for the cooling term. Okay, the cooling term is because the heat loss from the surface is going to be minus. Okay, minus, and this term, okay, from Newton law of cooling. So next is we can rearrange the form. Minus sign here is plus sign. Okay, it's gonna be like this. Then since delta x here, if the first term is very small compared to x, compared to here, x, so then we can ignore it, just like, you know, just ignore it to be 0, so it's gonna be x. Then if we divided e of this term with the x, dividing by the x, and take the limit of x to 0, okay, take the limit of this term, and rearrange the equation, we can get this formula, okay, which is equal to minus dqx times x, okay, qx is the heat flux, x is along the x term, x-axis over the x, minus t minus ta ambient temperature times 2 h is the heat conduction times h capital is the height of the fin over w, which is the width of the fin, cos theta, okay, equal to 0. Okay, now is look like it's gonna be easier right now after we reduce the form. Next is you substitute qx with the minus k dt over dx, which is the heat conduction term, the heat flux, okay, and you substitute here, okay, x, there's x here, dt over dx, and you rearrange k to here, okay, you know, you rearrange k from the heat flux, the heat conduction term to into this one because it's constant. We're gonna get minus d over dx, d of minus x dt over dx minus t minus ta times this constant term, okay, equal to 0, and then minus sign is going to be plus sign. So d of x dt over dx of dx here equal to t minus ta. We can we move this side to the right hand side. And then after we do the multiplication products, right? หน้าดิฟหลังบวกหลังดิฟหน้า we're gonna get x d square t over dx square plus dt over dx. Okay, then this one the same. Now it look like we have a second ODE, but not look like the form of Bessel function yet. Okay, so let's t minus ta equal to a function. Let's say y. Let's say y here, and 2 h small h times h over k w cos theta equal to alpha. Okay, so then if we substitute, like t here, when you do the differential, it's gonna be the same, because when you do the you diff d t minus ta is gonna be equal to dt over dx equal to dy, right? It's gonna be the same, so it's gonna be here is dy, d square t is gonna be d square y, and dt is gonna be dy, and here t minus ta equal to y, and the rest is a constant, which is alpha. Now it look like we have a second ODE, look like a Bessel function now, but we have to multiply x into the equation. So this one is going to be the Bessel form, okay, which is x squared times dx squared y over dx squared plus x dy over dx minus alpha x y equal to 0. So then we can use the Bessel method to solve this equation. Okay, to find the general solution in terms of Bessel function using the formula that I already showed you in the slides before, then we can compare the constant or the coefficient, and we figure out, and we got a equal to 1, okay, b equal to 0, c equal to 0, d equal to minus alpha, s equal to 1.5, and p equal to 0, and square root d over s is the imaginary number. Okay, so after you got these values, okay, I'm not gonna tell you in detail, and then you have to compare what the case of it. Okay, and we figured out this is case number 4. Okay, so that means the general solution of this Bessel form is going to be like this form, which is y of function x equal to c1 i0 0 here of function 2 times square root alpha x plus c2 times k function of 2 square root alpha x. Okay, this is the general form of the answers, which is the solution form in terms of series solution using the Bessel method. Okay, so we can also like get rid of a constant here, c1 or c2, and let's consider here. So now consider at the tip, which is x equal to 0. Okay, when we substitute x with 0 here, 0 here, it's gonna be k0 of 0, okay, and i0 of 0. Okay, so then the general solution above, and see that the table of i0 of 0 and k0 of 0, you will learn that. Okay, this is i0 of 0 and k0 of 0. You have to look at the table that I'm gonna give it to you in the folder. Okay, and you will learn that at k0 okay, at k0 at x0 is infinity, okay, k0 here is infinity, but y cannot be infinite temperature, right? Because imagine the temperature at the tip is not going to be like very high or very hot, so y here cannot be infinite temperature. So that means c2 here must be 0 because k here is infinity, so c2 must be 0, right? So that means this term we can get rid of it, c2, because c2 equal to 0. That means the general term, general solution is going to be yx equal to c1 i1 or function 2 times square root alpha x. Okay, this is the general form of this answer. And I at x and I0 at x equal to 0 is equal to 1. So C1 is a number depending on the value at alpha. So we have to keep C1. Okay, that's as I said. The final solution is going to be y or function x equal to C1. C1 is just it's going to be a number. We have to have a boundary condition to solve this. Okay, C1 times I0 of 2 square root alpha x. This is the final answer. Okay, and this is how we apply the Bessel function to solve second ODE in terms of uh, heat and heat transfer problem. So in the class, I will give you some examples that you can try and practice how to use a Bessel function to solve this kind of problem. Okay, I will see you in the class. Don't forget to review this video again and read the books. And if you have questions, let's ask me in the class. Okay, see you. Bye bye.